Okay, so let us begin the next session. We will continue to talk about coherence in this session as well. We try to right now till now we have talked about mutual coherence function, and then we talked about how we can normalize the mutual coherence function and find the complex degree of temporal coherence. In today's session, we will talk about how we can actually find the coherence time and move from a very perfect deterministic monochromatic light source to more practical light source, which is a Gaussian which is having a spectral distribution as a Gaussian. Okay, so yeah, so we talked about complex degree of temporal coherence, and now we actually discuss for a couple of cases. In one of the case that we usually see is a perfect deterministic light source. What do we see is that the gamma of tau, tau is the delay, is actually equal to I omega tau. And when we talk about the modulus of gamma of tau, it actually turns out to be 1. Right. So you can also try it out over here. How come this modulus of gamma of tau actually is equal to 1? Because if you see the exponential I omega tau, you can actually write it in the form of cos omega tau plus I sin omega tau. And if you talk about the modulus of I omega tau, that is nothing but the normalization of this one. So it's actually nothing but cos square omega tau plus sin square omega tau, and this actually is equal to 1. Right. So this is how the modulus of r or gamma of tau is actually equal to 1. Okay. So when we talk about perfectly deterministic light source, means you have a perfect sinusoidal light source. Okay, where is no variation in the change in the wavelength or in the change of the frequency as a function of light source. So this intensity versus time is kind of very perfect, right? And when you try to plot the modulus of r of tau, it happens so that it is actually the same, as it is actually turned to 1 for all the values of the delay, right. So autocorrelation of a perfectly deterministic light source is always equal to 1. But we don't have perfectly deterministic monochromatic light source in nature. What we have is a light source which is kind of having the same wavelength, and then it will come down, and then it will it will not be ever be a perfect monochromatic light source. So it will be something like this. And in this case, what you will see is that your r of tau, the modulus of your complex degree of coherence will be actually coming down as a function of the delay, right. It will start at 1, of course, because at tau equal to 0 it will be the same intensity, right, because you are autocorrelating with the same thing. But as you increase the tau, the degree of correlation would be decreasing with respect to the tau, right. Now let us talk about the coherence time. The coherence time is defined as tau c, is defined as minus infinity to plus infinity modulus of r tau the whole square d tau. Okay. So this is how the coherence time is defined. This is the coherence time tau c is defined as, and tau c is nothing but the time. So we will see now after some time how do you actually measure this coherence time. So there is an instrumental setup where you actually observe the interference plot or interferogram, right. So some kind of pattern. So time for the interference pattern to dissolve. So it will take, so if you move this a particular mirror, for example, so you will also, it's the movement of the mirror is actually correlated with the delay of the light that you are trying to autocorrelate with the original function. And this delay, how much delay does your function or this function can take, so that it actually kind of, there is no pattern that you actually eventually will see, right. So how much is the delay, or how much is the motion in that of that mirror that you can actually take, right. That is the coherence time. Similar to this, there is also coherence length. Okay, coherence length, that is defined by LC, which is defined as C into tau C. Okay. Now let us see an instrumental setup which could be used to quantify the coherence, right. Now what we do is, to quantify the temporal coherence, we use something known as Michelson interferometer. Interferometer. Right. So what do we do over here is that we give the light source from one side, and then we have a beam splitter. Okay, this is the beam splitter. Okay. What does the beam splitter do? There are some kind of ratios that they usually have. We can use a 50/50 ratio of beam splitter, which means that 50% of light it will reflect and 50% of light it will transmit. So 50% it will transmit, okay, and 50% it will reflect. Now I can have a kind of a mirror. Okay, this could be a mirror 1, and then I can have again one more mirror, can define as mirror 2, right. And the mirror, what it will do, it will actually it will reflect the light source, and again it will hit the beam splitter, and half of that light source intensity will actually propagate down. So this is one of the light source that is going to come back over here, and there is one more over here that will again come over here, and then it will come back over here. So there are two light source which are going to be coming over here, and it will actually give to a something known as a detector. Okay, so I will have a detector over here in the end. Okay, so this detector is going to eventually collect this light source, and now the both of the light source are on the same path. Okay, so if they are on the same path, they are going to superpose, right. So the superposition could be both. It can lead to a constructive as well as destructive interference. Okay, so now what we do is that we need to work with the delay, right. So main important part is the delay. So how do we involve the delay in this mechanism? Is that I can use a kind of a kinematic motion to this mirror 2. Okay, so I can move this delta x at a particular direction, and that will result into a particular time delay, right. The same wave that is given from the same light source, okay, but now it is having some delay because it has to travel not the same time. So the light which is interacting with the mirror 2, it travels more time before it reaches the the detector, right. So over here, for example, it in the first instance it travel x1, in this instance it also travels x1, okay, but at a later instance it's not going to travel only x1, but it's going to travel x1 plus delta x. Okay, so this delta x is going to result into the delay of tau, and this tau is what we are trying to correlate using the autocorrelation function. Okay, so this is the primary instrument which is used to quantify the temporal coherence. Okay, this instrument is known as Michelson interferometer. Okay. Okay, so now what we have been talking till now is a perfect light source. Okay, so this is the perfect light source, perfectly deterministic monochromatic light source. This is as a function of time, and this is the intensity, okay, or the electrical field intensity. Now, if I want to convert it into a Fourier transform, I want to do a Fourier transform. So, can you guess how will that look like? So, I have a W, which is a frequency, angular frequency, and then I have the magnitude of that Fourier transform. So, how would be the Fourier transform of a perfectly deterministic monochromatic light source be? You can just pause this video and then just think about it of how it should look like. Okay. So, what you will see is that it is actually a perfect line, like straight line, straight vertical line, right. For example, if it is a green light, so it would be, if it is a green light, it would be around 535 nanometers. Okay. If it is a blue light, it would be around 450 nanometers. If it is a red light, it would be around 630 nanometers. Okay. But in our real life, we don't get such kind of light source with a single straight line, right. So, what do we get? We get something like this. We get a spectral distribution whose typical wavelength or typical frequency is actually mentioned. So, usually we do not mention frequency, we usually mention wavelength. So, usually the okay, so over here instead of omega you can actually tell as lambda. Okay. So, the both frequency as well as wavelength are actually correlated. So, any one of that you can actually mention. Okay. So, this is the wavelength and this is the intensity. So, you have spectral distribution which is having some kind of a Gaussian nature. It could be a delta function to start with, which is kind of more simple, and then you can actually think it as a Gaussian function, as we will see in some time. Okay. So, we need that. Right now what we have done is we were finding the coherence time for such kind of monochromatic light source, right. But such kind of monochromatic light source does not exist, right. So, we need a kind of a Gaussian or a delta pulse. If we know the spectral distribution, can we somehow get the autocorrelation function? So, how does the autocorrelation function look like? It is nothing but gamma of tau. Okay. Then we do the normalization, and then we do the integration of minus infinity to infinity to get the coherence time, right. So, I need to move from a spectral distribution which is kind of Gaussian or a delta peak to an autocorrelation function. So, in this case one theorem actually comes to our rescue, and that is known as Wiener-Khinchin theorem. And what does it say is that what does it say that I can actually convert any spectral distribution into I can go back and forth. I can convert it into the mode of gamma tau, something like this, as a function of the delay. Okay. So, I can move from a spectral distribution to a autocorrelation function, and then I can move back from autocorrelation function to a spectral distribution as well. So, how do we do that? So, you can see that it is more or less similar to the Fourier transform. So, S omega is nothing but the spectral distribution. It is given as 1 by square root of 2 pi minus infinity to infinity gamma tau exponential I omega tau d tau. Okay. And when I do the inverse Fourier transform, I can get this gamma of tau, which is equal to 1 by square root of 2 pi integral of minus infinity to infinity. And here instead of gamma of tau, I get S of omega, the spectral distribution I omega tau d omega. Okay. So, if I have the spectral distribution, I can find what is the autocorrelation function of any of this spectral distribution. Okay. So now for example, let us start with a very simple monochromatic light source. Okay, let us start for a monochromatic light source. Okay, so now this is not a perfectly deterministic light source. So in mathematical aspects, it's kind of more or less used. So it could be a delta function. Okay, a delta function like having a the width tending to 0, right? So if you want to write this equation of this distribution, okay, so this function you want to write, you can write it as s of omega I into square root of 2 pi. So I is nothing but the intensity, and then it's of delta omega minus omega naught. So omega naught is nothing but the center frequency. Okay, and delta of omega. Okay, this delta of omega is nothing but the direct delta function. Okay, omega naught over here is nothing but 2 pi c by lambda naught, and this is nothing but the central frequency, central angular frequency. Okay, and omega naught is nothing but the central wavelength. Okay. So now so I have two equation now. This is the equation number 1, and my second equation is I want to find eventually the cross correlation, the autocorrelation function. So and I know what is s of omega. So this is my second equation. Okay, so I can put 1 into 2. I can put 1 into 2, and then I can find what is the gamma of tau. So what is gamma of tau? Gamma of tau is nothing but 1 by square root of 2 pi, and then instead of s omega I need to write this one over here, I into square root of, so I into square root of 2 pi delta of omega minus omega naught into exponential of I, this is I hope you understand this is I. Okay, let me just write it again. Yeah, this I omega tau d omega. Okay, so I can take this square root of 2 pi outside, and this is from minus infinity to infinity. Okay, and then this is a delta function. Okay, so if it is a delta function, you can understand that it is going to be something with only the exponential term. So you will, if you solve this further, you will get something like I into exponential minus I naught of tau. Okay, so gamma of tau is nothing but I into exponential minus omega of tau. Okay, now if you want to write the normalized function, so this after normalization. Okay, so as I told, once you get the mutual coherence function, you need to normalize it, so the maximum is actually equal to 1. So if you want to normalize it, in the denominator you get I, right? So here numerator has I, so the numerator I and denominator I gets cancelled, so you eventually had something like I omega naught tau. Okay, so this is your complex coherence function. Okay, which is the normalized of the mutual coherence function, and what we know is tau c is nothing but the coherence time is minus infinity to infinity exponential, and here it's actually, if you remember, it's mod of r of tau square, okay, d tau. So here if I put r of tau as exponential minus omega t naught, so you will actually see that exponential minus omega naught tau, the mod of this is actually equal to 1. Okay, as we discussed some time back as well, right? Mod of exponential of I omega t is actually equal to 1. Okay, so eventually we get minus infinity to infinity, and I get 1 over here and dt. Okay, so if I take integration of 1 with respect to the okay, this is not t, it is tau, okay, as a function of the the dt, you will see that it is actually tending to infinity. Okay, it's tending to infinity. So tau c is actually tends to infinity. So that is for a delta function. Okay, so for a delta function, the coherence time is kind of tending towards infinity. Okay, but again, what we have discussed till now is a monochromatic light source, and this is more or less in the mathematical world. Okay, this is not for for the practical world. Okay, in math world you can actually say about delta function and the light source adhering to this delta function, but in practical light source we seldom get any delta function, we actually get a Gaussian function. Okay, so so if you see, this is the light source in the math world, which is given by a delta function. Okay, but in our in our practical world, okay, this is the math world. Okay, this is the practical world. In practical world we get something known as Gaussian. So we need to understand what is the spectral equation of the spectral distribution of the Gaussian wave instead of the delta function, right. So if you want to talk about the Gaussian wave, how do we write the equation of a Gaussian wave? It could define as a into exponential minus of omega minus omega naught square divided by 2 sigma omega square. Okay. So here a is nothing but the normalized constant. So it's the constant actually. Here omega naught is the mean angular frequency. Okay, and sigma omega is nothing but the standard deviation of angular frequency distribution. Okay. So as omega is now given as not just for the delta function, but it is for a Gaussian function now. Okay. Now again we don't talk about Gaussian function which is not normalized. Okay. So we need to see how can we normalize this Gaussian function. So how do we normalize it? It actually can be normalized by giving as a equation like the following. So I can divide it by square root of 2 pi and sigma omega, which is nothing but the standard deviation, and in the numerator it would be the same thing, minus omega naught square divided by 2 sigma omega square, right. So this is for the normalized. Now it is the normalized Gaussian function. Okay, this is the normalized. Okay, now let us try to understand for this normalized Gaussian function, what are the different parameters that we need to take into consideration. Okay, so now let us again compare between the math and the practical world. So what happens in the math world? We compare, we define something known as sigma omega. Okay, sigma omega is nothing but standard deviation. But in practical world, so if you see any specific sheet, you actually see that it is such kind of Gaussian Gaussian function. You have the intensity 1 and its intensity, for example, wherever it is half of that intensity or the power, you define something known as FWHM, full width half maximum. Okay, so these are the two different realities. So in practice we usually use full width half maximum, but in the field of mathematics we use something known as standard deviation. Okay, that is nothing but sigma omega. Okay, this is what we have used, but in practice we use FWHM. So is there a kind of a correlation can we find between FWHM and sigma omega? so that if any of this function is or in any of this parameter is given to you, you can actually convert from one to the another, right. So there are derivations available. I will not kind of derive it, but you can also derive it at your end. So the standard deviation is directly proportional to FWHM, of course, and you can actually define as FWHM is defined as delta omega is defined as either it could be defined as the angular frequency or it could be defined as the frequency, right. So there are two ways you can define it. One is standard deviation of the angular frequency, square root of 2 ln 2, and then your delta nu, okay, that is the shift in the or the delta frequency, that could be given as sigma nu, okay. So one is angular frequency, another is the frequency itself, right. Okay, both the ways you can actually define. Here sigma omega can be defined as 2 pi sigma mu. Okay, so standard deviation of angular frequency can be defined as a function of standard deviation of the frequency as well. Okay. Now the next question comes to our mind is that usually that is what we have mentioned is in the terms of frequency. Okay, so you will find this FWHM not in the terms of frequency but in the terms of wavelength. So can we convert this frequency to the wavelength? So for example, if the bandwidth is given in terms of frequency, how can we convert it into wavelength, right? If the bandwidth is given in terms of wavelength, how can we convert into the frequency, right? So this FWHM is nothing but delta f in this case, okay, or it could be given as delta lambda based upon whatever is the parameter defined in the x-axis, okay. So that we can actually derive, okay. The way to derive would be you have c equal to nu lambda, that is nothing but c equal to f lambda, okay. Instead of f we talk in terms of mu, okay. So now nu is nothing but c by lambda. Now if I want to take the derivative, so I get d nu by d lambda is nothing but equal to c by lambda square, right. I negate, okay. So we can actually write it as del v, which is equal to c del lambda by lambda square, and hence we can write it as delta v, which is equal to c delta lambda by lambda square. So if we have a spectrum which is in spectral density, that is in the function of if we have a full width half maximum in the frequency spectrum, we can actually convert it to the wavelength spectrum now. Okay, so this is the frequency spectrum, and this is in the terms of wavelength. Okay, so in most of the cases you will find that in the specification sheet you will find that the source is specifically given in the wavelength range in the wavelength spectrum, and then in the detectors you will find that it might be given in both wavelength as well as frequency spectrum. The bandwidth most of the times are also given in terms of frequency spectrum. Okay. Yeah. So here the lambda that I am talking about over here, lambda is the central wavelength. Here delta nu, that is nothing but this delta nu is nothing but the spectral bandwidth, okay, and delta lambda is defined as a bandwidth. Okay, so here I am writing f, that is nothing but equivalent to nu. Okay, so but if you remember, the main aim that we wanted to do is that we just digressed it to discuss about a Gaussian wave, and that Gaussian wave how it is given in mathematical interpretation, that is given in the terms of standard deviation. Okay, and in the practical world you will see that it is given in the full width half maximum. But our main aim is to find the temporal coherence time, right? So that is how much time it is actually, we can say there is a significant degree of correlation, and that's what we want to find, right? So so to do that we remember back the Wiener-Khinchin theorem, and from that we can actually say that we have gamma of tau is given by 1 by root of 2 pi minus infinity to infinity s of omega exponential I omega tau d omega. Now for a Gaussian wave we define what is the spectral distribution. So if this is an omega, okay, the standard deviation is given by sigma omega, and this is spectral distribution. So I write s omega. So what is the so considering this s omega, if you remember this is the equation of the s omega, exponential minus omega naught square divided by 2 sigma omega square. Okay, this is for the Gaussian function, and this is not a normalized. So if you want, you can also consider the normalized function. Okay, so if you remember, the normalized is given by yeah, as you can see, this is the case for the normalized. Okay, this is the case for the normalized, and this is for the case for the actual Gaussian function equation. Okay, so we consider this equation, and if you substitute within this what we get, and then we also normalize this gamma of capital T, and what we get is nothing but small gamma of tau, and that is given as if you do this calculation you will find it that is equal to exponential I omega naught t into exponential minus sigma omega square tau square by 2. Okay, and we know what is the coherence time. So it's nothing but integral of minus infinity to infinity, and it is the modulus square of the modulus of gamma of small gamma of tau d tau, right? So this is the coherence time. Okay, this is the coherence time. And if you substitute this, you will eventually get your tau c to be equal to 2 into 2 into square root of 2 ln 2 by sigma omega. And if you substitute this sigma omega as what we discussed earlier using this conversion, okay, with frequency and wavelength, you will actually see that you are getting something like this: 4 ln of 2 lambda naught square divided by pi c into delta lambda. Okay, so this is the final equation of finding the coherence time for a Gaussian pulse. Okay, right. So this is the actual equation, mathematical equation that you actually derive once you calculate the actual equation for Gaussian function, and then you use this Wiener-Khinchin theorem to convert it into a autocorrelation function, and then normalize it, and then finally you can actually get the coherence time as a integral of square of the mod of gamma tau. Okay. So let us see this one nice example in the book by Caroline Borduch's Introduction to Biomedical Optics, Fundamental to Biomedical Optics. So in that she asks for two waves. The first wave is having a wave packet like this, okay, and then another wave packet is given like this, having a shorter and then it's asked that this is the tau, this is the real part of, and this is the maximum is around 1, then this is at 0.5. So it is asked, so so this is the wave packet generated by the laser source having the same wavelength. Okay, so there are actually two lasers, laser 1 and laser 2. Okay, but both of them are sharing the same central frequency. Okay, but their delta lambda, that is the bandwidth, is different for both the cases, right? So it is asked about which one is having a higher bandwidth and which one is having a lower bandwidth, right? So from our discussion, earlier discussion, you can find that your tau c is inversely proportional to your delta lambda, right? So you have tau c inversely proportional to delta lambda. So if your delta lambda is increasing, your tau c is going to decrease, right? So in this case, you can see that for the orange curve, okay, so the orange curve, this is the tau c, okay, for the green curve, this is the tau c, this kind of very small. So if you consider this is for the orange, okay, so laser 1 is for the orange and laser 2 is for the green one, okay. So what do you see? You see that your tau c for the green is less, while tau c of your orange pulse is kind of more, and that is why your delta lambda of your orange would be lower, while for the green it would be higher. We cannot comment on the exact value of this delta lambda, but we can comment which one is higher or lower. So bandwidth of the orange pulse is going to be lower as compared to the green one, right? Okay, so that's what we complete on the second session. So I will just summarize what we did. Yeah, so we started with the monochromatic light source as a delta function, right? So we started with S of omega equal to a delta function, and then we put it into your gamma of tau, and then we found what is the R of tau, and we after normalizing it, and then we finally found what is the coherence time, right? This actually goes to infinity for a perfectly deterministic monochromatic light source. But in our real life, we have a Gaussian function, so we don't have any perfectly deterministic monochromatic light source. We have some light source with having some kind of bandwidth or standard deviation, right? So we wrote the equation for the Gaussian function. We normalize it. And then we digress to understand what is the difference between standard deviation and full width half maximum. In the specification sheet, you will see that most of the time you will find full width half maximum, not the standard deviation. So you can actually switch from one to another based on this equation that we have defined over here. Okay, and then we also digress to discuss about if you want to shift from one spectrum, that is frequency spectrum, to a wavelength spectrum, so or the wavelength function, then how can you do that? So we actually derived it over here, and then we again went back to defining the autocorrelation function for the Gaussian laser pulse using the Wiener-Khinchin equation, and then we wrote the gamma of tau. Okay, and then we talk about the coherence time, right? And that's what we have defined. So this is the final coherence time for a Gaussian pulse. So we all know what is the value of lambda naught, what is the bandwidth, or speed of light, and all other the scalar constant numbers. So we can get it. We also talked about for two different light source, what could be different bandwidth if their center wavelength is the same. In the next session, we will talk about spatial coherence and how do you quantify that. Okay, thank you.